Okay, hi everybody. First, I would like to thank the organizers for this wonderful semester. It's a pleasure to be in IHP for some days, and also for this nice workshop, and giving me the opportunity to present this work, which is part of Maxime Vonneau's thesis, who is co-supervised by Nicolas Daubijon in Toulouse and myself in Lille. So the title is relatively long because we are at the interface between a kind of new theoretical framework for Bayesian inference, and also we want to be aware of the question of efficient sampling, and I will try to make connections between what is usually known in optimization as variable splitting, and the same kind of problems when you try to adapt this kind of approach to Bayesian inference and Monte Carlo Markov chain methods. I'm not sure it's working. Yeah, it's working. So first I will show you some images so that you are motivated for the rest of the talk. Then I will describe splitted Gibbs sampling and the splitted and augmented Gibbs sampling, which are the two main approaches we have proposed recently. And this last part is for maybe later discussion, but it contains the theoretical guarantees on the algorithms I will present here. So first, motivation. So here we are in an image processing workshop where inverse problems are at stake, such as image deblurring or image inpainting. So you know well these images. And one objective of our work is to have not only estimates of the reconstructed images, but also have confidence intervals so that we can assert that the estimates are, we can feel confident in our estimates. So these are already results we obtained with the method I will present now. Of course, we all want to solve big and large problems with excellent performances and be fast. But here, I will try to have all of these, of course, as everybody, and try also to have credibility intervals. This is our priority. And as subproducts of the proposed approach, we will also inherit some distributed computing possibilities and also some privacy-preserving properties. And this is made possible thanks to a Bayesian approach and MCMC methods. First, I go back to optimization and the ideas of variable splitting, and I write it in a already Bayesian-oriented way, since you see this f of x knowing y here, that is in general governed by the noise distribution. Y is the data, x are the parameters to estimate, and f2 of x will typically be connected to priors or penalty functions. Okay, and then you will very often hear about proximal operators, and splitting techniques consist in separating, for instance, the part f1 of x and f2 of z, depending on their properties, regularity properties, convexity, things like that, so that you can deal with them separately. And one way to do this is ADMM. We heard about this at the beginning of this afternoon, where you separate x and z into the two functions f1 and f2, and you have these other terms here which are constraining x and z to be as close as possible to each other. And the beginning of our work, the starting point was, can we adapt this kind of ideas to a Bayesian framework? In a Bayesian framework, the presentation is a bit different. Here we work with the posterior, likelihood, and prior, which are connected to their potential functions. So here I will talk about P1 and P2 as probability distributions, and F1 and F2 as minus log of P. And typically, in what people like to have in a Bayesian context are conjugate priors, but this is not always possible, in particular if you want to have rich models and very adapted to very specific situations. And for instance, we heard about TV, and TV does not give rise to easy distributions in the Bayesian context. A typical way to make inference using Monte Carlo methods, and a very basic method, is Gibbs sampling, which consists in simulating iteratively every component of the parameters x. So here you just throw random variables xi, knowing the others, okay, and also the data, of course. And you do this iteratively. And doing this large number of times, after some time you can show that you will have a distribution of values which follows the posterior distribution. Okay. Now the next step in the next slides, I will explain how we can do something like this to separate F1 and F2, so the potential, or if you want the likelihood and the prior, in two parts by imposing that they are, however, connected to the same final estimate. So x and z should give should contribute to only one estimate, which would be x, the variable of interest here. So first step will be splitting only, where you will see only x minus z and f of x, f of z, which will be the second part of the talk after these motivations. And third part, I will add another variable. So this will be data augmentation with this variable u, which will give some more freedom to the sampling method, some more better mixing properties. I will detail this in the following. Okay. Then, doing this, what we can expect is to deal with difficult sampling situations where we work with non-conjugate priors, so with complicated prior distributions, and also with big data sets or tall dimensions, so big dimensions, thanks to a divide to conquer strategy. So now I will talk about splitted Gibbs sampling, which I will shortly call by SP, and then split and augment Gibbs sampling, which I will call like SPA, SPA. And in the end, if I have time, I will say a few words about the general context of what we call asymptotically exact data augmentation, which is the more general framework in which we can incorporate both SP and SPA from a theoretical point of view. Okay, so splitted Gibbs sampling, it starts from the very simple idea. We have here what would be, for instance, a posterior distribution with this f1 of x connected to the likelihood and here to the prior. But this could be also, in a completely different context, any distribution that you want to simulate from. Okay, and then the idea of splitting is just separate f1 of x, f2 of z, and then couple them, for instance, by this square of x minus z. So in terms of diagrams, this is what we see here. So this would be the usual diagram with only f1 and f2, and here the augmented one, the splitted one. But in fact, this could be more general, and we could replace this L2, this square norm between x and z, this distance between x and z, by any divergence that is controlled by some parameter rho here. So this is the control parameter we will have to deal with in the sequel. But first point, since we are working with distributions, the first assumption we need to do is that this coupling will not modify the final distribution, so that the marginal of x for fixed rho, so I will say later on what is the role of rho, but for the distribution of x, so after marginalizing the new variable z, should be something close to, in the end, what I called pi of x, which was my initial model. So depending only on f1 of x and f2 of x. Okay. So the first thing we have to impose to phi rho is that you can choose any divergence between x and z, so that when rho tends to 0, you are back to a Dirac, so that in TV norm, then p rho will tend to pi as rho tends to 0. So this is what we call asymptotically exact model. Okay, so this is to be very general, but in practice we will very often and most often use the quadratic norm between x and x minus z. Okay, then the conditional distributions of Gibbs sampling. So the two distributions you will have to simulate from will be pi rho of x knowing z and pi rho of z knowing x, which will have, after splitting f1 and f2 in two parts, we'll associate this phi rho with f1 or phi rho with f2. So two distinct distributions. And there is a very special case which is of interest. That is when we use this L2 norm between of x minus z, because then here, if you think of optimization, you see proximal operators coming in the game. And then you can think of proximal MCMC methods introduced by Pierre and studied by Durmus, Moulin, and Pierre recently, and which provide us with efficient methods to simulate Monte Carlo Markov chains in situations where the priors are difficult to deal with. Or after splitting also, if here you imagine that we have Gaussian noise, here you will have again something which is an L2 norm, and we are back to Gaussian variables, and then we are back to a question of how to optimize the simulation of Gaussian variables. But you have separated the contribution of F1 and F2 in two parts, and Gibbs sampling becomes much simpler. If you deal with inverse problems, so let's go for a very concrete and simple example. For here, the observation is the observation matrix is P, and we want to recover X knowing Y, and N typically is Gaussian white noise. So F1 would be the L2 norm. Here, psi of X is some penalty. And then the two conditional distributions we get from this splitting ID are a Gaussian with some QX here. I didn't explain it in details, and psi of Z here. Okay, let's see what happens with using TV. So you can see what happens with Tikhonov regularization here. You will go back to Gaussian variables. So this is a simple case as well. But here we will use, for instance, TV for deblurring. And then go for proximal MCMC using the algorithm introduced by Marcelo Pereira and others. And okay, so the posterior distribution is a combination of the Gaussian and TV. We want to do this in a high dimension. There is no conjugacy here, so just for those who are not familiar with Bayesian approaches, conjugated priors are such that the combination between the prior and the likelihood give explicit posterior distributions so that we can deal with them easily. So here are some results of this TV deblurring using proximal MCMC and splitting. And I will explain what we gain. So this is the result. Okay, fine, it works. But what we have gained is that now we can, since we are using Monte Carlo methods, we not only have estimates, but also a distribution of the values inferred by the sampling algorithm. So that here what you can see is, for instance, that where in very regular regions, the error bounds are very small, while around edges, you have confidence intervals which are much larger. What about, what have we gained doing this? So what we have gained is that first, the result. So just in pure performance, don't worry about the fact that it's better or not better compared to the behavior, the neighbors. In some cases it's above, in some cases it's below, but it's comparable with what you would get using Salsa, for instance, or what you would get using PEMULA, which would be the usual, now the usual Monte Carlo method to deal with this kind of problem. What is important is this, the fact that here, if you directly use this proximal Monte Carlo method, it will take like 8 times the computational time that you have using splitting. Because using splitting, you have much better mixing properties, you have a much simpler algorithm for simulation, so that the computational time is strongly reduced, while keeping good performances and gaining these confidence intervals or credibility intervals. So that now you not only have an estimate, but also a level of confidence in this estimate. Yes, then going to some more technical details for those who are familiar with Monte Carlo methods. One thing which is important is the correlation between two successive samples. And here what you can see is that using directly P-mula, which is the proximal Monte Carlo method, and after splitting, so this is the autocorrelation function of the Markov chain, you can see that it's very fastly decreasing to 0 here, much faster than P-mula. While we are still using P-mula. I must mention that we are not saying P-mula is not good. We are just saying split and then use P-mula. Okay? And just the fact of splitting makes P-mula much more efficient. If you look at what is the role of this parameter rho, so the rho is the coupling between the now two variables x and z, because we have splitted the problem in x in two parts. Okay? You can see that in red is the evolution of the cost function. Oh, sorry, it's f and j, so since it's f1 and f2. And in red, it's the evolution of the cost function for P-mula directly applied to the initial problem. So using the true posterior distribution pi of x. And in blue or green, so blue or green encodes the value of rho going from very small to much larger. What you can see is that when rho is very small, which would be ideally the exact model, because when rho is going to 0, we recover the initial model asymptotically. What you see is that the algorithm does not go very fast to the solution. It goes to a good solution, but very slowly. Now, if you increase this value of rho, you give some more freedom to your samples, and now you let x and z vary each one on each side, and have some freedom in exploring the state space. And the gain is that this curve goes down, so that the computational time to access good estimates is much shorter. So the message here is that this parameter rho is a kind of relaxation parameter, which allows you to play with a compromise between computational time and quality of restoration. So you can give up part of the quality of the restoration if you want to gain some computational time. When I go to now splitted and augmented Gibbs sampling, so which would be the equivalent in the Bayesian framework of ADMM, which is well known in optimization. We want to do this because we want even better mixing properties in cases where the inference and the Monte Carlo simulation is very difficult. I will show an example just after. So now we have two more variables. So you start with p of x, and now you add z and u. So z is as before. So you can see here f of x and g of z. It should be f1, f2. So you still have the equivalent of what I called phi rho before. So you see phi1 depending on rho. And in the same spirit, we will add a variable u so that z is connected to x, but with some more freedom again. It's like a spring that allows x and z to move one around the other. And phi2 with parameter alpha will tune how far x and z are connected. Okay. Then we have to obey some assumption on phi1 and phi2 because we are in this Bayesian framework and working with probability distributions. So that marginalizing u, we should recover finally the splitted problem. So SPA after marginalizing u, which is this new variables we have added in the game, we should come back to SP, so splitting only. Yeah, I think this is clear now. So what about the conditional distributions? So again, in the very general case, you will see f on one side, g on the other one, this coupling term phi1, and a third distribution, which is for this u variable we have introduced, this augmented data term, where you can see phi2 and phi1 combined all together in the same exponential. So now, of course, there is a natural choice, which is the L2 norm, so that Gaussian distributions appear again. So for this step, it will be very simple, Gaussian distributions. And for the other steps, again, we can see typical cost function connected to proximal operators. And in the case where f of x is again an L2 norm, it's again a Gaussian variable. Otherwise, again, use Pemula for simulations. We could have used Pemula from the beginning. But again, this strategy of splitting and augmenting the problem while enriching it, in fact, make it much more efficient for inference. And if you take at each step the map of each of these distributions, what you get back is just ADMM, exactly. So this is also an interesting observation that the connection here between SPA and ADMM is just direct. In the case where you use a TV regularization, here it will be for inpainting in the following example. So you find back my P observation matrix, X for the original image, and this TV term regularization, and the three marginal distributions where you can see the term coming from the data fidelity, thank you, term, the TV norm for regularization, and this Gaussian term which comes just from all these variables we have added due to splitting and augmentation. Then in Pemula you can embed the state-of-the-art algorithms for optimization. So here for inpainting, so this is with I think 65% pixels missing. This is the estimate. So here I talk about MMSE, so minimum mean square error estimates. And again, we get from these samples we can get confidence intervals. All of them are numerically estimated until now. Have a look at the performances, and we compare with SALSA, and we see that in terms of pure performances, SP and SPA compare with SALSA, while Pemula alone didn't. While here, we still use, again, I insist, we use Pemula, but embedded after splitting and augmenting the model. And then we recover SALSA performances plus confidence intervals. We have considered a series of problems, so you can adapt them, and including problems in machine learning, but it's not the question here. And so to illustrate SPA in a situation which is very specific and difficult to deal with, so Poisson noise, and where we propose to use SPA plus Pemula, combined with Pemula, what we gain is a factor 6 in terms of computational time. Moreover, there is no approximation in the model because due to splitting, we can work with each term separately and keeping it exactly without using, for instance, Anscombe variance estimates and things like that. Performances are comparable with optimization results, and we get confidence intervals. So here is the restoration and confidence intervals. Again, you can see that, of course, edges are much more difficult to restore than flat regions. Okay, I see I have time, so I can talk about now the main problem once you have nice techniques like this. For now, until now, I have shown only numerical results. I have said, okay, it works. I have confidence intervals, but they are all estimated from Monte Carlo samples, Monte Carlo method samples. And I cannot be sure that these are really confidence intervals or credibility intervals. On top of that, I work with an approximate model. So I have added this rho parameter and even this alpha parameter, which says that the posterior distribution I am simulating in the Monte Carlo Markov chain is not exactly the model I had at the beginning. So it's a new model, which is an approximation of the initial model, which asymptotically will converge to the exact model. So what we are dealing with now is theoretical guarantees about what we have done until now. And then we move to a framework which is in fact, much more general than what I've presented until now for inverse problems. And this is connected to the simulation of any law of this kind, exponential minus f of x. And now I can have in mind that this f of x will be likelihood plus prior, or it will be over a network with many nodes, and it's a sum of cost functions, or a combination of distributions. So pi of x can be, depending on the different situations, a prior or a likelihood, posterior. Here you can think of ABC methods, for instance. There are many, many connections. I won't present them all today. The only thing I will keep in mind is that pi is difficult and possibly inefficient to simulate or to sample from. Okay, this will happen very often. And the first very usual strategy, which is reminiscent from the expectation maximization strategy also, is data augmentation or latent variables. Then the idea is to add a new variable, z, so that you can have a new problem in which you have separated the problem in several sub-problems with this divide to conquer strategy idea. Okay, the only condition is that when you marginalize z, you should recover the initial model. Exactly. This is called exact data augmentation. Then what you expect, what you hope doing this is, or what you target is an augmented likelihood, which is easier to work with or easier to compute, for instance. It's also a joint posterior with simpler full conditionals. Then you are thinking of, you think of Gibbs sampling, for instance. And also mixing properties I mentioned before, which more technical point, but which is crucial for the quality of the Monte Carlo method. Then if you want, if the target is an exact data augmentation, it's very difficult to find the right distribution or the right way to pass from pi of x to pi of x and z, so that you get these nice properties. So the first problem is find pi of x and z. And then we also have in mind the problem of going to big data, so a large number of observations, or tall data, so maybe not so many data, but in large dimensions. So the idea I've presented you until now, talking about SP and SPA, so split and augment Gibbs sampling, are a way to relax this exact data augmentation constraint to go to something which is much more general, much easier to implement, and efficient, and with guarantees. So first thing, what I want is to build some p row of x and z so that I get pi row of x as a marginal, and asymptotically, pi row will tend to pi of x. And here on this slide, you find again the same theorem as the one I showed at the beginning of this talk. We want some approximate model, and asymptotically exactly recovering the initial model. Okay. Now, taking inspiration from optimization, I motivated this before. We explore this idea of splitting in a very much general context, which with the objective of simplifying inference, maybe distribute it in the same spirit as ADMM permits to distribute computations over nodes, for instance, and of course, accelerate the inference. To the same, we need to be sure that we have some nice properties so that proximal Monte Carlo methods can be used. So this is the reason why you see again this question of long concavity and differentiability and conditions on expectations and variance. These are rather technical. What is much more important now are the following results. First result, a bound on how far, what is the speed at which this pi row goes to pi. So how far are we asymptotically exact and which speed? And detailed computations make appear this complicated function, which is a parabolic cylinder special function, okay? don't worry. What is important here is that if you look at what happens when rho tends to 0, is just a linear behavior in LF, which is the Lipschitz constant of the first potential function here. So here there is only one, so it's LF, the Lipschitz constant, and rho, the approximation parameter. This picture shows you how far it depends on D. So this is encoded, sorry. This is encoded in the behavior of this special function here. How does it depend on D combined with rho? So this picture shows you that when rho tends to 0, we recover this linear behavior. So this is as a function of rho. We have here an upper bound on how far the TV norm between the distribution of the initial model and the distribution of the approximate model are the TV norm of the difference between these two distributions. So this is an upper bound on it, and when you are in dark blue, it's for small dimensions. Of course, for light blue, we are looking at larger and larger dimensions so that you see the bound growing and growing, but not growing so fast. Depending on the function you have chosen, the rate in the dependence on the dimension can be between square root of d and d to the 3/2, which is not so much. So the increase here with the dimension is not so big. You see that it's logarithmic here in the dimension. So what we can hope doing this also is to deal with very high dimensions. This was one of our first challenges. I won't explain this now, but a dual of this property is also that if you work with a likelihood with big data, you can also split this likelihood, and you have the same kind of behavior, so that this splitting strategy will be also efficient for dealing with a big number of observations. The two or three next slides are on the way to bounds on the credibility intervals, because I showed you in practice that we have credibility intervals coming from the empirical distribution of the Monte Carlo samples. But now what we want is to have theoretical guarantees on these numerical credibility intervals. And this can be computed. The first step is consists in controlling the difference between the two potentials, so the approximate potential and the exact potential, the original potential. So recall that here I talked about a distribution which was exponential minus f of x, and now we are talking about f rho of x, which is an approximate potential, after integrating the distribution against some Gaussian distribution here. And you get two bounds, a rho and u rho, which can be computed explicitly, and have a nice behavior. I don't show them on graphics. I go to the credibility intervals, which can be deduced from these bounds I just showed you. So now if you compute what is the probability that the observed value, the initial model give value in the credibility interval C alpha rho. C alpha rho are the credibility intervals on the approximate model. Okay, so my question now is, if I predict credibility intervals from the approximate model, how far do I get credibility intervals that are compliant or consistent with the credibility intervals I would get from the initial model? Okay, so the bound you see here are on this quantity, that is the initial probability integrated over the approximate credibility intervals. And we have theoretical guarantees here, so a lower and upper bound, which are gathered in this table. So on the left, the rho parameter. So of course, when rho tends to 0, we should recover the initial model. So the first line should be very good. So what we can see here is are the bounds of the interval given by the bounds. Okay. So what you see here is that when rho tends to 0, here 10 minus 2, we can see that the probability, so these are 95% credibility intervals, okay? we see that we recover this 0.95 proportion probability, and the bounds are very close to 0.95. So asymptotically, these bounds tell us that this level of confidence deduced from the exact model, but using samples from the approximate model, are very fine. In practice, we will very often be in this region. Why? Because we want fast inference. So we don't want to choose rho too small. We want to choose rho bigger to be faster. So in this table, of course, you can see the compromise. The higher the line, the closest to the initial model you are. And lines at the bottom are associated to faster computations, but more approximate. The bounds are, of course, then wider on a theoretical basis. However, in practice, what happens is that it's very close to the real value you wanted to recover. And here are pictures which show you the evolution of pi rho towards pi for various value of rho, so for 10 minus 2, 10 minus 1, and 10 minus 2, 10 minus 1, and 1 for rho. Okay, so that you can see the effect of the approximation varying rho. How much time? 5. Okay. So then, last point before my conclusion, I mentioned before that one interesting property of the splitting approach could be very similar to the gain of ADMM approaches, that is distributed computation and maybe privacy preserving approaches. And here is an example where, I will show you this before. Yes, I'm starting from this model for logistic regression, for instance, and I want to make logistic regression on different data sets, so which will be called DJ, and there are B groups of data. So DJ are are associated to the JS block of data. So the data is distributed so that we can hope to preserve some data privacy and no sharing of data between users. Sorry. I just said not disturb, but okay. So now the splitted version of this consists in adding these ZJ values. So for each data set, each subgroup of data, we will introduce a new variable ZJ, so that you can see these splitting terms or coupling terms between the target parameters and coupling variables or augmented variables, ZJ for each subgroup. And here is the typical cost function for logistic regression. Then we can use a Gibbs sampler distributed on B nodes, get estimates with credibility intervals again. But the master nodes never sees the whole data set, so that privacy is preserved. And moreover, what I did not mention a lot before, this idea of splitting the data can be used also for distributed computing in general. So you have, again, everything I showed before on computational time was not using parallel computing. It was just using the algorithm in a sequential implementation. So there is still time to gain by parallel implementation or distributed implementation. So as a conclusion, the main messages are inspired by ideas from optimization. We have explored what could be done by a split and augment strategy in a Bayesian framework, thinking of MCMC methods for inference, and targeting confidence intervals to have not only good estimates, but estimates with credibility intervals. Then we want to use efficient algorithms, and splitting is a very good idea for this, because then you can use state-of-the-art algorithms either for Gaussian variables or combination of Gaussians with covariance matrices which cannot be diagonalized in the same basis, for instance. You can split them in two parts, and also it can be distributed. So you can use state-of-the-art algorithms so that you accelerate inference, and it can be distributed. Moreover, on a theoretical basis now, this, so what we call this AXDA, like approximately exact data augmentation, gives us a unifying statistical framework. I didn't mention this today, but there are connections with nearly all Bayesian approaches which can be reformulated in this AXDA framework, which explains, for instance, robustness in some situations. So we discover ABC from some point. And also we have, and this is not the least, non-asymptotical theoretical guarantees on estimates and confidence intervals. Thank you for your attention.
Yes, thank you.
I forgot to mention that if you want to play with it, Maxime put everything on GitHub.
Okay. Is there some questions?
I was wondering how many iterations of Mueller do you do for every, in SPA, you know, how many iterations of Mueller do you do for each iteration of the Gibbs sampler?
I showed this on this, I have a table on an example. Okay. 10 to the 4 here. 10 to the 4 here in this case. This was for deblurring.
So that's the number of iterations of Mueller?
Yeah.
In each iteration of the
No. Iterations are per Mueller.
You do only one?
Yeah.
Okay.
There is no, it's embedded. When I said embedded, it's with the meaning that you take the initial problem, split it so that you get a new one, and then you are back to usual strategies for sampling. When I say usual, for situations with irregular priors, I think of proximal MCMC.
Okay.
Thank you.
If you want to know more about proximal MCMC, I think it's on Thursday.
I was wondering if, so with Euler you have a gradient term and a prox term, but it depends on how you implement it. And usually what constrains the performance is the Lipschitz constant of the gradient term.
Yes.
Whereas prox operators, they
Yeah.
are Lipschitz with constant 1.
Yeah.
So I was wondering if the performance gain comes from the splitting itself or from just the fact that proxies are implicit steps, so that they basically you don't have stiffness in your chain anymore.
Okay, another property you get from splitting is that the Lipschitz constant, which appears in P-Euler, is no more the Lipschitz constant of f of your cost function. It's 1 over rho square.
Yes.
So now rho also, why rho controls the speed of the sampling, it's also connected to the Lipschitz constant, which controls the P-Euler algorithm.
Okay, so I just had a question like related to my talk, because it seems, you know, at least for ADMM and, you know, convexity is a big issue, like the infinite divisible, they're almost never convex, the potential function. So is there some hope?
Yes.
Yeah, so we need to talk, okay.
A few months, a few months more.
Oh, okay.
But this is typically a natural question.
Yeah, so like, because they're very heavy tail.
Yeah.
Yeah,
but
you think there's a solution?
I'm not sure, but it's a good question.
Okay. So let us thank Pierre again.
Thank you.